All right, welcome back. We are going to start Chapter 6 in Sullivan and Sullivan's pre-calculus book on trigonometric functions. And we're going to probably spend the rest of the year studying trigonometry in this class. When we start section 6.1, angles and their measure, you guys are going to need to spend some time doing a little bit of reading through the textbook and probably taking some vocabulary notes on your own before you get. So you may want to actually stop the video now and instead get to your textbook and look at all the bold vocabulary that's available to you. Any that you're not familiar with, you want to write down a definition. You want to get used to using these words. If you're comfortable with the vocabulary that you see presented in that section 6.1 at the beginning, then I'll go ahead and use it as we start our lesson today. Okay? The very first thing that we're asked to do, really just to use the vocabulary, this is before any of the objectives are given, is we're asked to graph or sketch a graph of some angles in standard position. So the first angle we're asked to graph is a 45-degree angle. We know that if we're going to graph this in standard position, we need the initial side of the angle on the positive x-axis. That's the portion of the x-axis to the right of the origin. And then we need the terminal side of the angle to be a revolution of 45 degrees in a counterclockwise direction to give our terminal side. So here's a picture of the 45-degree angle in standard position. Remember, the vertex of an angle in standard position is going to be at the origin. Now, when you graph your angles or sketch them, you do not need to label initial side and terminal sides in words. But you can label the angle measure, and you do want to show the direction of revolution there. Again, because this is a positive angle measure, we know that we're going counterclockwise. Objective 1b asks for a negative 90-degree angle. If we want a negative angle measure, we need to make sure that our revolution goes clockwise. So, vertex at the origin, initial side on the positive x-axis, 90 degrees of clockwise rotation to get our terminal side. Go ahead and pause the video and get these two pictures into your notes. Alright, coming back. The next angle we're asked to sketch is a 225-degree angle. Once again, vertex at the origin, initial side on the positive x-axis, counterclockwise rotation for a positive angle measure, 225 degrees terminates in quadrant number 3. Also want to show you here another way that I can label my angle measure. Rather than writing the measure by the rotation, I've put it out by the arrow at the end of the terminal side, and that's acceptable as well. Last of the four angles we're going to draw here is a 405-degree angle. Interesting thing, obviously, this is more than 360 degrees, so we have more than one revolution from our initial side to our terminal side. When I sketch that, I'll show that revolution by starting the revolution on the positive x-axis, returning once to the positive x-axis, and then continuing on. So if 360 degrees returns me to the positive x-axis, I need another 45 degrees in addition to that to get my total of 405 degrees. So this angle terminates in quadrant 1. Go ahead and pause the video. Make sure you have the pictures you need for parts C and D. Alright, that was just to work some vocabulary. Now we can start with our actual objectives. So the first objective that we're going to look at is the ability to convert between decimal and degree, minute, second measures for angles. So obviously we know things don't always occur in whole numbers, and if we're looking at the portion of a degree, we can do that with decimals, or we can do it with what are known as degrees, minutes, and seconds. We want to be comfortable with both because both have real-world applications. Okay? So, we know that one counterclockwise revolution is 360 degrees. It's a positive number because we're going counterclockwise. All right, you guys know about 360 degrees. All right, we can look back in history for why we've chosen to divide a full revolution into 360 degrees back to the Babylonian times and their idea of the Babylonian calendar having 360 days in a year. A lot of connections between trigonometry and astronomy like that. If we want to break one of those degrees down further, we break degrees into minutes. 1 degree is 60 minutes. And please don't confuse minutes of time with minutes of angle measure, even though the number 60 is common in both of those. Breaking down our minutes further, 1 minute can be broken into 60 seconds. Again, this is not a measurement of time. Okay? These are just fractions of degrees. So example number 2 is going to have us do some converting. They're going to want us to convert 50 degrees, 6 minutes and 21 seconds into a decimal. Okay? In order to do that, again, remember that minutes and seconds are fractions of a degree. And so I'm going to rewrite this 50 full degrees. I had 6 minutes, but I know each minute is the fraction 1/60th of a degree. I had 21 seconds. Because a second is a 60th of a minute, and a minute is a 60th of a degree, then I'm going to need to square 1/60th. There are 1/3600ths there for our degree measure. Simplifying this, just arithmetic. We can use a calculator for some of that. Okay. This is approximately 50.1058 degrees. We were asked to round to 4 decimal points. Okay. We can also convert the other direction. Why don't you pause this and make sure you have part A, and then we'll convert something from decimals back to degrees, minutes, and seconds. All right. Part B, we're going to begin with a decimal. 21 and 256 thousandths of a degree. When we do our conversion, obviously we know we have 21 full degrees, and then we have 256 thousandths of a degree. That's a portion of a degree. The reason I've chosen to write it like this, where I'm multiplying by a degree, is now I can use my conversion factor, and I know that 1 degree is equivalent to 60 minutes. So there's no difference between the value of these two expressions. Going ahead and simplifying by multiplying my decimal by 60, I end up with 20 degrees plus 15.36 minutes. So now I have degrees and minutes. I'm basically going to do this process a second time to deal with the portion of a minute. So now I'm going to write this, just like I did above, as 36 hundredths of 1 minute. I know that 1 minute is 60 seconds. So again, these are equivalent, and multiplying there gives me 21.6 seconds. When I write my answer, the directions ask to round to the nearest full second. So that's why my answer to match the book is 21 degrees, 15 minutes, 22 seconds. Go ahead, pause the video here, record example 2. Although I'm not going to go into it on this video, you can use your graphing calculator to do both of those conversions using some commands in the angle menu, and that's something I encourage you to explore as well. Continuing our study of angles, the next thing we're going to look at is we're going to look at the idea of a radian. Now, you've studied radians, I hope, at some point in your past, but I'll treat them like you've never seen them before. Okay? A radian is a different way of measuring angles. Okay, it's just a different unit. Okay, we love radians as we move forward into calculus. Radians are real numbers, and we can use radians as the input for functions. Okay, so the definition of a radian is that if an angle on a circle of radius r subtends an arc length of r, that angle is 1 radian. So I'm going to show you a picture here. Okay? In this picture, I've got a circle of radius r, and I've drawn an angle that is subtending an arc length equal to the radius of the circle. So that is also labeled r. If the angle makes this arc length equal to this radius, that angle is 1 radian. Okay? The second objective, now that we've talked about what 1 radian is, we're going to really use radians for a lot of objectives. Here we're going to find the arc length of a circle. So I'm going to start you with another picture, and I'm going to look at a proportion here. So we know from our studies in geometry that central angles in a circle and the arc lengths that they subtend are proportional. So in this picture, I've just drawn 2 arbitrary angles. Each one has its vertex at the center of a circle, and each one subtends an arc length on the circle. And these 2 angles and the subtended arc lengths have to be proportional. So don't worry about scale of the picture. Let's just work algebraically with the proportion. If I define one of my angles to be 1 radian, and I've chosen that, then I can substitute that 1 into the proportion. When I do so, based on my definition up above, I know then that the arc length I subtend has to be the radius of the circle. Over here, dividing by 1 is an identity, so I end up with this, that the theta, the angle measure, is equal to the arc length subtended over the radius. This is an incredibly important equation. Remember that in order for me to do this, I had to be working with radian measure. This does not work with degrees. Go ahead and pause the video here, record the definition of 1 radian and the formula or the equation for finding that radian measure, arc length divided by radius. All right, continuing right along. The objective said we would talk about arc length. All I've done here to define arc length is taken my equation from above and solved it for s. Multiplying both sides of the equation by the radius gives me this equation. The arc length subtended by an angle is equal to the radius of a circle multiplied by the angle measure in radians. Don't forget we're in radians there. Those 2 equations are the same thing. This one allows us to calculate angle measure. This one allows us to calculate arc length. Right? Let's put that one to use. Example 3 in our textbook asks us to find the length of an arc of a circle of radius 2 meters subtended by a central angle of 0.25 radians. Since I have my radius and I have my radian measure, I'm just going to substitute into this equation above. There's radius, there's theta, and I'm going to multiply. Okay? Now you'll notice when I wrote my substitution, I wrote my unit of measure for the radius as meters. That was given. I did not write a unit of measure on my radians. Let's talk about why I can do that. If we back up to here, radian measure for theta is the quotient of an arc length and a radius. Both of those are lengths and can be measured in the same unit. When I have a fraction with the same unit in the numerator and denominator, I can divide those units out, and then I just have my quotient of these 2 values. What that means for us is really radians are unitless. We do not need a unit on radians. We can write the word radian if we want, but the truth is, like I said earlier, a radian is just a real number. Go ahead now, pause the video and record example 3. All right, moving right along. Objective number 3, the ability to convert from degrees to radians and from radians to degrees. Obviously, if we have 2 units, we want to be able to use either one as situation dictates. So let's talk a little bit about our knowledge of 1 full revolution or 1 full circle. In a full circle, we know that the circumference of a circle is 2 times pi times radius, right? Circumference equals 2 pi r. So, in our equation from before, where arc length equals radius times the central angle in radians, if I substitute the arc length 2 pi r, remember that would be the arc length for one full circle. Dividing both sides of the equal sign by the radius tells me that 2 pi equals the central angle. So, for one full circle, the angle is 2 pi radians. So, one revolution equals 2 pi radians. We already knew that one revolution was 360 degrees, so the conversion factor between degrees and radians is that 360 degrees is equal to 2 pi radians. If we want to simplify that, we can divide both sides of the equation by 2, and 180 degrees is pi radians. Notice that those radian measures are irrational. We said earlier that radians can be real numbers. Real numbers include rational and irrational values. So these are irrational radian measures. If I want to solve either of these equations for a single unit, I can choose to divide both sides of the equal sign by 180, or I can choose to divide both sides of the equal sign by pi, and that gives me these two equations. These are really important, so I've highlighted them for you. Okay? Dividing both sides of this equation by 180 tells me that 1 degree is equivalent to pi over 180 radians. If instead I divided both sides of this equation by pi, then 180 degrees over pi equals 1 radian. Go ahead and pause the video here, record this information so we can convert between degrees and radians. All right. From here, our next two example problems are going to have 5 parts each, and they're going to be a series of conversions. We know we can do unit conversions by multiplying fractions and dividing out common units. So, example 4a from your textbook asks us to convert 60 degrees into radians. So I've written this as the product of 60 times 1 degree. Now, I'm only going to show this step in part A. It's one that we can basically leave out once we understand the process, but I showed it here since it's new. 1 degree is equivalent to pi over 180 radians. That comes right out of this box here. If I multiply, obviously I have a common factor in my numerator and denominator of 60, so reducing this gives me pi over 3, and that's my radian measure. Remember that radians are unitless, so you can choose to write the word radian after your answer here, but you're not required to. Also notice, this is another irrational measure. We do not have to have an irrational radian measure. We started our whole discussion with a measure of 1 radian. That's a rational number. But frequently we will have irrational radian measures. Also know that I could choose to approximate this if I wanted to using my calculator, but there's no benefit to doing so right now. We can leave our exact answer. Pause your video and record example 4a. Then use your textbook and on your own, try examples 4b through 4e. Alright, so I hope you tried the rest of this example on your own. I'm only going to go through one more, not all 5 parts. Example 4b, we worked with 150 degrees. Remember that a degree is pi over 180 radians. Here I have a common factor of 30 in my numerator and denominator, so when I reduce this I'll get 5 pi over 6. As I said, I'm not going to show the rest of the parts here, or at least I'm not going to talk through them, but I will show them so that you can pause the video and check your work. Here's B, C, and D. Here's part E. I did mention earlier that we had irrational values for a lot of our radian measures. I chose to approximate this one just to show you that I can do that on my calculator. 107 degrees is just under 2 radians. Okay, we didn't take the time to approximate all of them, but I wanted you to know you could do that. Pause the video to make sure that you have example 4E in your notes. Continuing right along, example 5. In example 5, we're just converting from radians to degrees, going the other direction. So 5a, we have pi over 6 radians. This is pi over 6 times bigger than 1 radian. Remember that 1 radian is 180 over pi degrees. And simplifying that fraction, the common factors of pi and common factors of 6. Divide out of the numerator and denominator. This is 30 degrees. Go ahead and pause the video, record example 5a, and on your own, do example 5b through 5e. There's examples B, C, and D for you to check your conversion. Here's example 5E for you to check your conversion. Again, notice on 5E I did approximate my answer. I certainly could have stopped right here. Okay, 3 radians, which is a rational number, is equivalent to 540 divided by pi degrees. That's approximately 172 degrees. I hope this answer seems reasonable to you. We started our exploration here by saying that 180 degrees was pi radians. This is just less than 180 degrees. 3 is just less than pi. All right. Example 6 is going to get us into some pretty cool connections between trigonometry and the world around us. Okay? Here we're going to look at latitude and longitude. And you guys have probably studied latitude and longitude in a geography class, but here we're going to learn about it from a math standpoint. We're going to actually learn what the numbers mean. So latitude is formed by creating an angle whose vertex is at the core of Earth's center. The initial side leaves the core of Earth and passes through the crust of the Earth at the equator. And the terminal side leaves the core of Earth and passes through whichever location you want to locate using latitude. Okay. In this problem, we are asked to examine Sioux Falls, South Dakota, and Dallas, Texas, and the latitudes of each of those 2 cities are given. We are also told that those 2 cities are approximately on a north-south line. Sioux Falls is directly north of Dallas, so we can ignore longitude in this problem. The only other piece of information we are given is we are given the radius of Earth at 3,960 miles. With that, we should be able to calculate the distance from Sioux Falls to Dallas. So the first thing I'm going to do is I'm going to find the difference between their 2 latitudes. That tells me the angle between the cities. So subtracting their latitudes gives me 10 degrees 47 minutes. Now 10 degrees 47 minutes isn't going to work for my needs because I need to convert this into radians. Before jumping right to radians, I'm actually going to convert the minutes into a decimal. So this is approximately 10.7833 degrees. And then I'm going to convert that into radians using the conversion factor we just practiced over and over. So the angle between my 2 cities is about 188 thousandths of a radian, right? 0.188 radians. Now we're going to be able to go pretty quickly. The distance between these two cities is just the arc length along the Earth's surface. Arc length equals radius times theta. Remember, the radius was given to us by the book's author as being approximately 3,960 miles. Here's theta, the angle between my cities. This is unitless. Radians don't need a unit. And doing a quick multiplication tells me that the distance between these two cities is about 744 miles. Since this is a word problem, I'll answer it with a complete sentence, showing that I truly understand all about it. Pause the video here. It's going to take a little bit of time probably for you to work through and understand example 6 about latitude. All right, you guys are doing a good job. All right, we're most of the way done. Fourth objective in this section, as we review lots of trigonometry, is to find the sector area of a circle, or the area of a sector. Now remember, a sector is sort of like a piece of pizza. All right, a sector is bounded by two radii and their included arc length. Okay, there's that piece of pizza there. So earlier we talked about proportionality in circles. So I'm going to look at proportionality again. I've drawn two arbitrary sectors, each with a central angle, one labeled theta, one labeled theta sub 1. Those two sectors each have an area. I labeled them A and A sub 1. And we know from our studies in geometry that this is a proportional relationship between the central angles and the area of these two sectors. For our needs, I'm going to say that we're going to examine a sector with a central angle of 2 pi. Right? Now, if a sector has a central angle of 2 pi, what does that mean about our sector? And that means it's the full circle, because 2 pi radians is one full revolution. Therefore, if this is a full circle, we know the area of a full circle is pi times radius squared, right? Area equals pi r squared. I can substitute those two things into my proportion from above, giving me this equation. If I multiply both sides by pi r squared, that will isolate A, and this can be reduced by a factor of pi on top and bottom. So I end up with 1/2 radius squared times theta is equal to sector area. Once again, for this to work, theta has to be in radians. Right? What we've done is we've derived this sector area formula that the book gives you. Notice I've just written it again. Area of the sector equals 1/2 times radius squared times theta, where theta is in radians. Pause the video and record this introduction to sector area. All right. An example problem for sector area, going to go really quickly. Okay. Example 7 in the book says, find the area of the sector of a circle of radius 2 feet formed by an angle of 30 degrees. Round the answer to 2 decimal places. So here we have our radius and our central angle of 30 degrees. The only way this problem is going to give you any headaches is if you forget that theta needs to be measured in radians. So our angle of 30 degrees has to get converted using our conversion factor from earlier. That's pi over 6 radians. Once we have the pi over 6 radians, then we can use that in our formula. So here's actually where we're working. The area of our sector is 1/2 radius squared times theta, which is 1/2 times 2 feet squared times pi over 6. Have to be in radians there. That's not optional. Simplifying that gives me 4 pi over 12 feet squared. The only unit in this problem was on the radius, because remember, radians are unitless. This can be reduced by a factor of 4 in the numerator and denominator, so the area of this sector is pi over 3 square feet. If we need to approximate that, that's just bigger than 1 square feet, 1.05. The directions asked us to round to 2 decimal places. Before you pause that, I'll slide the beginning on there. You see that whole thing? There we go. There you can see my work where I converted my angle to radians and then used it to find sector area. Pause the video and record example 7. Alright. Last objective. Find the linear speed of an object traveling in circular motion. Now, we know all about linear speed. Even listening to just reading the word makes us think of going in a line. Okay? The way we find linear speed is we go distance divided by time. Think about linear speeds like in your car, miles per hour. That's distance in miles divided by time in hours. Okay? But we can also use linear speed for motion around the circumference of a circle. We can travel in an arc there. So, linear speed equals distance over time. On a circle, the distance we would travel is the arc length. And we can divide the arc length by the time. In variables, we use V equals S over T. S is our traditional variable for arc length. I used it earlier in our video. I don't think I addressed what I was using S for. T is our time. The other type of velocity we need to examine, though, is we need to examine something called angular speed. Okay? Since we're traveling in a circle, there's also the ability to measure the angle that we pass through divided by the time it takes. We need a new variable for this, and we happen to use a Greek letter here. This is the Greek letter omega. Okay? When we say that omega equals theta divided by t. All right? This is the angular speed that we travel equal to the angle that is swept divided by the time. Pause the video and record our definitions for linear speed and angular speed. Last thing I'm going to do with these is I'm going to connect the two together. So when we connect linear speed and angular speed, there has to be a connection between those two on a circle. I'm going to begin with my definition for linear speed, arc length divided by time. Earlier in today's lesson, we said arc length was radius times theta. Based on my rules for multiplying fractions, I could write that as radius times the fraction, theta over t. The reason I would do that is because I'm familiar with that fraction. We just said theta over t was the Greek letter omega. Doing so shows us that the linear speed of an object traveling on a circle is equal to the radius of the circle times the angular speed of the object. That's a really important thing to know. All right. Last example we're going to look at today, we're going to find linear speed. We have an example of a child swinging a rock around at the end of a string. It says a child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. Find the linear speed of the rock when it is released. So here's my known information. The radius of the rope is 2 feet, and the angular velocity is 80 revolutions per minute. Now a revolution is an angle, a minute is a time, so we do have angle divided by time, but what unit do we really want to use for angles? I hope you said radians. So we're going to convert this. This is my omega, 180 revolutions in 1 minute. I'm going to do a unit conversion. My conversion factor is I know that 2 pi radians is the same as 1 revolution. I've got a common factor of revolutions to divide out, and that leaves my units being radians over minutes. So this is 360 pi radians per minute. You will get the chance to do that frequently in application problems. Convert revolutions per minute to radians per minute. Now, Linear velocity equals radius times angular velocity. So v equals 2 feet times 360 pi radians per 1 minute. Multiplying here gives me 720 pi feet per 1 minute. Again, remember, radians are unitless. So my unit in the answer, or in the numerator, is feet, and the denominator is minutes. A lot of times when we write this, we're going to convert it to a more accessible unit. So when we talk speed, there's nothing wrong with feet per minute, but it might make more sense for people to convert this to miles per hour. That's just more comfortable with what we know. So I've done my conversion factors. 1 mile is 5,280 feet. 60 minutes is 1 hour. Then I can divide out both the feet and the minutes, leaving me only miles and hours. This is approximately 25.704 miles per hour. Miles in the numerator, hours in the denominator. The linear speed of the rock is about 25.704 miles per hour. Please pause the video and record example problem number 8. All right. I know we threw quite a bit at you there. There's a lot of vocabulary in this section for you to become familiar with for angle measure. And then there's a lot of different equations or formulas that we used along the way. So take some time to practice these for sure, and we'll get you working with a lot of them as we get further into Chapter 6. Have a great day. Stay healthy.